Yeah.
Okay.
So, let me give a brief introduction about Sir before we start the session. So, Sir is currently working as a geospatial consultant at Well Labs, where his primary focus is on research impact works in water security and water accounting space. Sir is also working on climate change impact on forestry and water bodies. So a significant aspect of Sir's journey in this remote sensing field was his master's thesis, integrating SAR and optical data for crop classification in Gauribidnut Taluk. And Sir had an opportunity to implement on a live project, YesTech, which stands for Yield Estimation Through Technology at Karnataka State Remote Sensing Application Center. So YesTech is a new technological initiative under the Pradhan Mantri Fasal Beam Yojana, Ministry of Agriculture and Farmers Welfare, to empower farmers. So Sir has worked in the development and design of the workflow using Google Earth engine for data acquisition, algorithms for crop classification, and yield map generation for 13 districts of Karnataka. Uh, Hearty welcome to you, sir. Uh,
Thank you,
yeah,
ma'am.
over to you, sir.
Yeah. Is my voice audible?
Yes, sir. Yes.
Okay. I'll present my screen. Okay. Is it visible now?
Yes, sir.
Is the slideshow more visible?
Yes, sir. It is now in slideshow.
Okay. You can just see the slides, ma'am. It's all right now. It's
Yes,
using
yes, sir.
Google Slides. Okay. Namaste. Very good afternoon to the August gathering here. Today, it's a great honor and privilege to address all of you in this faculty development program, having a broad spectrum of artificial intelligence in satellite image processing and application. The topic I'll be dealing today is integrating remote sensing with AI for smarter agriculture and water use. We know remote sensing has a great ability and a boon with multidisciplinary approach in addressing various problems. And now here at the cusp of this revolution, we are in a very hard stake where we are addressing two major issues, that is the food security and water efficient technology usage. So here the main topic which I'll be dealing with it is the integration of artificial intelligence and remote sensing for a better, a smarter agriculture and a effective, smart, efficient water cropping and cropping systems, as how well we can integrate the technology and have a better results. So the basic structure of this presentation would be in such a way that I will be covering a basic of how AI and remote sensing can be integrated, specifically in the agriculture domain, the water use. Then we'll have some in between time for discussion. Then I will move on to the specific case studies where I approached with the live projects that I handled in my career tenure. So it would be a more of an interactive session than one-way speaking. So we can have a better discussion and exchange ideas. Let me start. So let us take the global scenario now. Global demand for food is rising. Can we meet it? This is by the Harvard Business Review, which was done in a decade ago. It was in 2016, where the food security is a major crisis in the globe due to the population rise, and there is a potential decrease in the farming profession, and there is a gap between the production, the consumption, and the intervention between the technology that is used for effective harnessing of the food security on a global scale. So, taking this scenario and moving forward, in the year 2050, will the technology be able to feed the world's population is a big question. So, how how can we think in this regard with the multiple perspectives is what we see first. There are complex challenges in the world. We have many problems, and the problems are interrelated, and one problem having a solution, that solution leads to a greater problem, and the complex challenges are intervened together. Second is the data science. There are multiple data from multiple sources, and getting the data is almost 50% to 60% of the work done in the total project. So we have to have some data science where there is there is an integrated approach where we can have multiple data from multiple sources and have an effective data product developed. And there should be a holistic monitoring. So this is what the stack stands for. It is spatio-temporal asset catalog. So not only the holistic monitoring is on a spatial scale on a ground level, but also on a temporal profile that combined together form this stack, spatial temporal asset catalog. So there should be a holistic monitoring of the whole technology that we are trying to implement. The holistic monitoring characteristics should be implemented in the technology. Then the resource optimization plays a major role because resource optimization not only in terms of the hardware, software, even the human resource and the technology and the SDG sustainable development goals that gets pitched into it, and how effectively can we do. For example, if we take the chat GPT and if we query a simple question here, we might be getting wonderful answers, but the background processing, the system that it utilizes, the VM it has is very huge. So it is vast amount of energy spent. So there should be an effective resource optimization also to be taken into account. Then after this, after having all this, there is data explosion. There is big data. We have huge crunch of data. And with this current trending technology, the data is vast. But we should find an effective way where we can harness it in such a way that the storage capabilities, the computing capabilities, and the outcomes are in a very readable format. The final is everyone needs an automation. The manual, the traditional thing, everyone are fed up with it, and the trending world is more on an automation. So the technology should be in an integrated approach of all this. So when we see the whole synaptic view of this, the first thing that comes to our mind is artificial intelligence, machine learning, deep learning, neural networks, and many other stuff. But actually, in the recent news statement, the Nobel Prize winner for the year 2024, who was a pioneer in the foundation of artificial intelligence, feared that AI will eventually take control. Yeah, someone is unmuted. Can you please mute yourself? So there is a fear that artificial intelligence will take control of the whole world or on a global domain where we can't foresee things. But before this, we have to have such a mindset where we can take control of artificial intelligence, the various technologies, and address the global scenarios. So here the global scenario we are addressing is the food security and the water resource. So let me go to these artificial intelligence. In the past 5 days in the FTP, I've been a participant, and most of them have covered the overall scenario of how the broad perspective of artificial intelligence, machine learning, neural network, deep learning, how one is correlated with the other, how the overall mapping is done. So I won't spend more time on this. This is just a general view so that we get our foundation strong. And from past 5 years, eminent scientists, professors have dived deep into it. So I'll keep this very short so that the stage is set and we'll move forward on a more on an application oriented information. Okay. Now, coming specifically to the topic, AI techniques in remote sensing. So, the artificial intelligence in remote sensing, where all, on a broader perspective, the remote sensing plays a key role in remote, where all the AI technique plays a key role in remote sensing is what we first look at. The image classification. The image classification is here assigning the label to the feature or the category is a broad spectrum that deals with the image classification. The second is the object detection. Here we identify the object and we put a bounding box to it. That is the one-line definition of the technology of object detection. The third thing is data fusion. As I said in the previous slide, the data is very vast and we have multiple data sets from multi source. So artificial intelligence in addressing data fusion is also a very good application in terms of remote sensing. The fourth one is semantic segmentation, where we segment the whole imagery into classes or types, which is a more advanced form of image classification. The most interesting thing here is the anomaly detection. So what does this anomaly detection do? So when there is a point or a data set which deviates from the whole of the group, so that is taken out as an anomaly and that detection is done. So this basically addresses many of the scenarios where pest detection, crop health monitoring in that scenario. The next one is the feature detection. The feature detection is data is huge and the raw data has to be converted to a readable format. So the feature detection, the extraction effectively converts the raw data, whatever we are having, to information. The another thing is the time series analysis. So what does this time series analysis mainly deal with? So as I mentioned, the spatio-temporal asset catalog, we have series of data on a temporal scale. So time series analysis has huge chunk of data and the vastness amount of data is unimaginable. So AI techniques of AI can be implemented in this regard in specifically in remote sensing. The final is the modeling and simulation that involves all of this together in an integrated approach on a problem specific scenario. So now let us dive deep into the AI applications in agriculture. The primary AI application, whatever we see, whatever we have heard in the past 5 days, is all crop classification. So we have set of images acquired from different sensors, different dates. We train the model with the ground truthing. We get a crop plan. This is the application in crop classification. The second one is the yield prediction. Yield refers to how much amount of crop is harvested from a field. So where we can use multiple tools in of AI such as CNN, ANN, machine learning, where we can dive deep, where we can give the inputs of various parameters that is affecting the crop and result yield out of it. So these two parameters, these two applications, I will dive deep into it because this is the practical, the case studies I will be addressing in this today's session. The next one is the pest detection. The pest detection, as I discussed, it comes under anomaly detection. So when there is huge farm and the monitoring of farms becomes a huge task. So there should be a synaptic approach where we can monitor from a distance and we can actually pinpoint where the crop is affected so that a time-based health monitoring can be done. So this comes under the pest detection. The fourth is the soil health monitoring. Soil health monitoring scenario is where we monitor the soil characteristics in terms of the nutrients, the moisture content, and that would comprise together to form soil health monitoring. From the remote sensing perspective, we have various index which can be obtained from the remote sensing, and that applied on any AI models can effectively predict or give a time series analysis of the soil health monitoring as at what point of time what nutrient or what type of irrigation or what water needs to be supplied into the field can be done using the under the scenario of soil health monitoring. The most important and the trending topic is the carbon sequestration. Because of the global scenario of climate change and the temperature with the carbon emissions, more than the forestry carbon sequestration, now people are more focusing on farmland carbon sequestration, where the farmers are paid to grow certain crops that can absorb carbon and they get the carbon credits out of it. So this monitoring can be effectively done using the AI tools. Now, speaking about the food security, this precision agriculture is an effective application of remote sensing integrated with AI. Precision agriculture mainly deals with how precise the inputs for agriculture and how well the whole farmland is monitored. The next scenario is the agro-meteorology. Here we deal with agriculture, the meteorology, which it's on a climate scale, the rainfall, humidity, temperature. All this data goes as an input, and we have a agroclimate model where we can say at this climate scenario, this crop or this type of horticulture gardens might have an effect. So what mitigations, what uh, uh, what precautionary measures can be taken in hand and protection can be given so that there is no loss of crop. So that is under the agrometeorology section. The next is the climate adaptation strategies. This is even in the yesterday's talk, we were quite discussing in this regard. The climate change has massively struck the whole world in various industries, and climate change adaptation strategies is a niche area in still because the as I was saying, the anomalies in the climate is very difficult to predict out. But with the support of AI and a backup with the vast amount of data, we can develop an effective model where we can develop adaptive strategies in order to counteract the climate change. The global monitoring is from nation to nation. The exchange of food goods is quantified in terms of food security. So we can have a holistic digital agriculture system around the world where we can say this part of the region grows this much amount and this part of the region grows this amount of other crops. So how well the exchange of goods in terms of crops can happen is the global monitoring scenario which I'm specifying here. The final thing is the disaster assessment and mitigation. We have seen the floods or the droughts have hit to a huge extent in past a decade. Reoccurring of these two major catastrophes have shaken the lives of farmers. So, in terms of disaster assessment, with the ground-based technology won't have a proper control of assessing the disaster or mitigation. So, a sky-based, satellite-based, or a drone-based technologies can be used where this AI models trained from the previous historical data sets would give quantify the disaster in a better way, and the mitigation approaches can be effectively done pinpoint to the locations where actually on the ground the land has been affected. So now let us have a a broader, a more deeper perspective on how this big data AI can be used in agriculture domain and how this two integration would lead to better advantage outcome. So we have big data, which supports when incorporated in digital agriculture. Incorporating big data aids in support for smart farming, which involves uh, smart control and big data in the cloud, smart analysis and planning, and smart sensing and monitoring. All this, all these three categories falls under the smart supports smart farming. There is a noise in the background. Yeah. Then artificial intelligence in agriculture. Now, in order to have a enhanced decision making, we have to deal with the issues faced in the agriculture domain. That is mainly the soil issue, the pest detection, and the crop monitoring. So we can use AI technologies in order to solve all this together, and that would come under the whole branch of enhanced decision making. So when we combine this big data and AI, we can overcome challenges, we can optimize supply chains, we can boost efficiency and increase the productivity. So this flowchart found to be interesting, so I have taken it from this reference. This gives a broader picture where we stand in terms of utilizing both big data and artificial intelligence for digital agriculture or smarter agriculture. Next is the AI application in water use. So we know in the global scenarios, and it is predicted that there would be wars for water. So there is a need where we can monitor water resource and utilize it in an effective and efficient manner. The first thing is the water resource mapping. Water resource mapping mainly deals with mapping the water bodies, the extent of it, and having a time series profile as how the water bodies were filled in the past years and what is the trend in, and how it is meeting the water needs of the surrounding community or the society and how well the utilization of water takes place in irrigation, whether it is over irrigated or it is less fed. All this blockchain technology needs to be monitored, means we should have the water resource mapping, and water resource mapping is a challenging task, whereas using of remote sensing gives a very precise and synaptic workflow for developing water resource mapping. The second one is the irrigation management. As I mentioned, the water fed to the farmland is the crop harvested. So the water productivity is how much water you feed into the agriculture and how much yield is resulted out. So water productivity is can be quantified as the yield per water supplied or the amount profit obtained per water supply. So these two comes under, as we have the crop productivity, that is how much yield we estimate out, how much yield we extract out of a field. We have this crop water productivity, where how much amount of water we supply and what is the harvest obtained. So this is under the irrigation management. The third is the groundwater monitoring. This groundwater monitoring in the context of artificial intelligence is a very challenging subject because the ground dynamics totally differ, and this is not a very uh, with the given amount of resources we have, this area has a very good chance of exploring more scenarios in the future trends. So groundwater monitoring plays a very crucial role, both not only in terms of satisfying the water needs, but also on an environmental and a disaster field. The next one is the field flood prediction. So this comes under the disaster management approach, where we see the flood events happening very frequently in the past decade. So how what is the spread of the flood, and what farmlands have been drowned by the floods can be effectively mapped out using the AI technologies integrated with remote sensing. So now, taking into the context like monitoring disaster is a very big challenge, and the rescue operations would also be very hectic. But when you use remote sensing that integrated with AI makes this job easier is what that is being experienced and what the whole world is venturing for. The next one is the early warning system, taking the water demand and the supply into the context, and if an effective model can be developed where we can say at this season we are there is a high chance that we might hit a drought. So prior to 6 months or 1 year prior to this, we can effectively plan in such a way that the water quantity is distributed in a well resorted way, that there won't be any need for taking supply from the external sources. The more important thing is the water quality assessment. So remote sensing having various indices where if we could calibrate those indices with the IoT devices on the ground, we can effectively monitor the water quality. It is not just how much water we have, but how much water is consumable. So the water quality assessment plays a very crucial role in terms of human life, environment, and the water body environmental impact assessment. So the water quality assessment can be easily mapped using the remote sensing technologies with the integration of AI. The reservoir management is a subset of the irrigation management and water resource mapping, where this reservoir management, when integrated with the agriculture, gives us an effective crop water productivity. So integrating all this together, we get this crop water productivity. So crop water productivity is what I explained, what amount of water we supply and what is the yield obtained in terms of, it might be in terms of kgs or it might be in terms of income. So this is the general overview of AI applications in agriculture and water use. So the next part I will be dealing more with it is with the practical application. So before I go into it, let us keep this session interactive. So these are the Sentinel-1 SAR images of Sentinel-1 SAR data with the color scheme of VV given to the red, VH green, and VV by VH to blue. So as you might have heard from PP Nageswara sir, the 8 elements of image interpretation, the size, texture, pattern, associativity, and the rest of the things. Can you identify what are these water bodies? So yeah, what rivers do these images represent? You can comment or you can unmute and speak.
What happened, Raghav? Continue.
I have, no, sir, I have given them some task of
Oh,
identifying these water bodies. I'm waiting for
oh,
them.
okay, all right. Okay, okay.
Okay, I will give a 1 minute of time. Yeah, yeah, the ones which are dark are the water bodies. So looking at this, okay, okay, let me not spend more time here. Let me give out the answers. So this is the Ganga, this is the Tungabhadra, and this is the Kaveri. So why I brought down this image is before we make the system understand what we are trying to do, we have to have a broader perspective in an interdisciplinary approach as what represents what. So here we are having the color feature, pattern, texture, tone, and the associativity. Associativity. If you see in the Tungabhadra, whatever you are seeing is shiny gray patch like a spear is the Sandur cyst belt that is actually blocking the Tungabhadra, and the engineers have effectively designed in such a way that this geomorphological unit is giving strength to the dam. And the third one is the Kaveri. So you can see this is the KRS structure, and with whatever magenta purple color you see around is all the croplands in the Mandya and the Mysore district, mainly of paddy. The first one is the Ganga. You can see how rich green she is. Yeah, so we have to have a interdisciplinary approach when we speak about remote sensing, because it is not only the domain if we know geology or environment or agriculture. No, we have to have an integrated approach so that we can make the machine understand, or once the machine spits out some output, we are able to interpret it. So this was just a simple exercise I wanted to share. So now let me go to the context of the use of AI and remote sensing in a smarter irrigation system. So what does this smarter irrigation system do? So it has mainly two things, that is the digital tools and the sensor. This is on a ground level that that supports the data analysis and real-time monitoring. On a global scale or on a synaptic view, the monitoring methods here, whatever red plot you see, here the satellite data, the remote sensing, the UAV approaches can be integrated. So soil-based monitoring that monitors the soil water potential and soil water content. This effectively using the UAV or the drone technologies, we can effectively monitor the soil water potential and soil water content. The second one is the weather-based monitoring, where the meteorological variables on a global scale is obtained out, and this goes into the model of the smarter irrigation system. If there is more heat, or when the temperature is high, or when the humidity is high, what amount of water needs to be supplied to what crops. This input is obtained from this branch of the irrigation systems. The next one is the plant-based monitoring, which is the plant water status. So, based on the crop phenology and the reflectance from the plant, we can assess. Example, if we take the land surface water index, we can assess how much water moisture content is present in the crop and what is the requirement with the atmosphere around and what must be supplied. So if we have this integrated approach as an inclusive approach together, we can effectively monitor the entire farmland and have a smarter irrigation system. So what does this effectively give as an advantage is efficient water use. So efficient water use promotes us in having promotes us in environmental protection, which leads to the improved yields, which reduces the cost. And finally, our scenario is the water conservation. Whatever I told, the food security and the water conservation is met. So having this AI as a right arm and remote sensing as a left arm, and if we work together, if we could combine these together in the context of agriculture and water resource, we can meet the global scenarios and we can effectively destroy all the negotiations of having food threat issues or there is a threat for water. So now let me dive into the applied case studies which I dealt with. So the first one is the crop classification. So this study was done in Gauribidur Taluk. The data sets used were SAR data and optical data. SAR stands for synthetic aperture radar. This is from the microwave, and the second one is the optical data set. So these two data sets are obtained from the Sentinel satellite. So the data sets were stacked based on studying the crop phenology as which dates should be effectively chosen. Because when you take a Kharif season from June to October, November, there might be 12 images in total, but we should effectively pick out images where you can see soil. It is in the adult stage, mature stage, and it is in the harvest stage. If we could get 3 points where that is actually having an impact on the whole crop phenology, then the data set is optimized. So after we chose effective dates, all the stacking was done, and normalization of band was the second step which was followed. For this, we ran a random forest algorithm based on the ground truth, which I went to the ground and I collected thrice. So it was in the month, it was during the Rabi season, whatever we did. So I went twice. That was when the crop was in the mature stage and it was in the harvest stage. So this ground truthing samples were given as the training to the random forest algorithm. After that, the performance and evaluation of the model was done with the test samples we had, which were kept apart from the training, 70 training and 30 for the test samples, and the evaluation of model was done. So the final output obtained here was the classified maps and area estimation. So this is the overall approach of this case study or of the project which I had done. So now, but here this is an overall approach. But why integrating SAR and optical is a big question. So here, if we see during many people say remote sensing is a boon, but the villain here is the clouds. So when you take in the Kharif season, the optical data is totally torn apart due to the cloud cover. We can't effectively monitor the crop during the Kharif season due to the cloud cover. That too, typically in South India, we have seen vast amount of challenges due to the cloud cover. So if we see on a same date, if we see the SAR data, see SAR data is having an advantage. This is from the microwave spectrum, so it can surpass the cloud, it can penetrate the cloud, and it can obtain the information. But one thing we have to remember is the optical data speaks about the crop phenology, the biological aspect, but the SAR data speaks about the information on the biological aspect. State. So the idea of integration was from this reason where we can we integrated SAR and optical data sets upon which the classification was done. So the optical that were taken, the data fusion were done in terms of principal component analysis. So the first there were two principal component analysis done. One for the optical data because we had 11 bands of data ranging from red, blue, green, NR, and so on. And with the SAR data, we had VH and VV band. So typically resulting in the first three components of the principal component derived from the optical data with the VV-VH band of the SAR data, and upon which a data fusion was done where 3 PCA plus PH and VV were taken. They were trained into the model based on the training and the data set, and the classification was performed using the random forest algorithm. And I won't specifically deal with the more specification on random forest algorithm because this is most of you would be familiar to it. So here, my main motive today is to say you the problems and where we can use which technology to solve the problem is what I want to say. So after this, we did the post-classification analysis. Then we obtained the classified maps and area estimation. So this is the general methodology that was employed in generating the crop map. So this is the outputs. This is the crop classification map generated for MSI dataset, the optical dataset. You can see different crops: banana, maize, mulberry, and there is a fallow land. Water body forest pair built up. There was a crop mask that was put to the data before it was classified. So these classes weren't under the training or in the evaluation here. So this is the outcome from the MSI dataset. This is the crop classification map obtained from the MSI dataset. Similarly, independently, SAR dataset was also used and the crop maps were obtained. It resulted out in a little 2% less accuracy, that was 70%. And you can see the area estimations out of it. In SAR datasets, the various band there are no bands here. So we used VV, VH, and VV by VH as band combination, and we did the crop classification upon this. This is the SAR multi-temporal composite. Multi-temporal composite refers to the different dates of image acquisition. So 3 dates of image acquisition, as I told during the crop sowing, the mature and the harvest stage, 3 images were taken, upon which after stacking all this together, forming spatio-temporal asset catalog, we generated this crop classification map. You can see the overall accuracy is more because a single date image would give information only on the date, and differentiating one pixel with the next pixel on a single date is little difficult to the algorithm because it doesn't have that much of parameters where it can develop some equations to differentiate one from the other. But when you take the multi-temporal composite into the consideration, it has, for every pixel, it has three features. So it can easily differentiate and it can cluster which pixel is representing which crop and which pixel is representing the other crop. So this multi-temporal composite as an add-on advantage in the whole scenario of crop classification. This is also, you can witness it here, how the accuracy has increased. The next important thing is the fused product, where I mentioned the SAR and optical. So the SAR and optical fusion was done using the PCA, upon which the classification the algorithm, the random forest was run, and this is the crop map generated out of it. and you can see a greater 80% accuracy is obtained. So why not multi-temporal optical composition is done might be a question, because as I mentioned, due to the cloud cover, getting images for more than two dates is very difficult and very challenging in terms of optical data set. So that couldn't be experimented with the multi-temporal composite optical data set. So you can see the SAR and optical fused data gave a very good accuracy, and even the interpretation of the components were in such a way that it was like seeing a segmented model output. So this fusion technique overcomes the challenge of the availability of non-cloud free data, availability of cloud free data during the Kharif season. The second one is the integrating the crop phenology and physical parameters of the crop growth using SAR and optical data set. Another part of the study was the crop phenology monitoring. You can see this NDVI, normalized difference vegetation index. It is an index developed from the red and NIR band, where it typically speaks of how the crop growth is happening. The spectral reflectance is measured and this index is obtained. So NDVI was developed for five major crops grown in Gauri Bidnar Taluk. So you can see, for example, if you take maize, you can see it was in the month of, let us interpret this graph for some time. In the month of mid-May, maize was sown. It reached maturity in the month of October. Then it was harvested in the month of November, and it was left fallow. You see the graph, it tends to go down. It is going down. It is here, it is raising. That shows there is a crop phenology, there is a crop growth. And when it goes down, it is harvesting. And from November to February, it was left fallow. Again, in the month of February, the second crop was taken in the field. And when you see mulberry, you can see mulberry, this profile, the box profile, you see this pattern, a wave, typical wave with some rise in the steepness of the curve. This wave pattern is due to the trimming of the mulberry. Mulberry is supplied to the silkworm, so every now and then they prune it, they feed it. So you can see a rise, a dip, a rise, a dip, a rise, and a dip. So this is the mulberry profile. And next is let us see the paddy profile, which is very interesting. So this is the paddy profile. The field was left fallow. There was no crop taken until November. Then in the month of November, a single crop was taken, that was the paddy, and it was harvested in the month of February. So you see, and even the peaks of various crops differ. So this act as an effective tool in identification of different crops with this NDVI trends. And you see ragi peak is too low, and this dynamics of peaks, rise, fall, and the temporal scale. So now you might be getting an idea why temporal data sets were chosen. As I keep on stressing upon the temporal composite done, because if we take say if we acquire an image on say November in this point, in the month between November and December, you see all these things intersect. So there is no interpretability of the data. So we have to have a crop window where we can see, if we take a image in the month of September, you see all these profiles are differing from each other and there is no intersection. So we have to choose dates also effectively in such a way that whatever data, whatever the junk fed in is the junk output is what we get is a well-known thing. So we have to have a proper understanding of the crop phenology before developing the crop maps. So this is a case, this is a study where we can do the crop phenology monitoring as at what stage the crop is in what time. So from which we can predict out at what time it would be harvesting and at what time it will come to the market. So what would be the price tag that can be given? Or if there are no crops in that domain, we can encourage farmers to cultivate it so that they can get a profit on a later part. So this is the crop phenology. This is using the optical data. Now, in the same way, using the SAR data, also we can have the crop phenology monitoring. This is based on the backscatter, VH profile and VE profile. So if you see here, because as I mentioned, the SAR data more on a crop phenology. It deals with the physical parameter. You can see the dynamicity here. If we take the banana VH profile, is the banana is the blue color with the dots, and if you see the mulberry, which is the red, it is having a similar rhythm profile. So you can't easily differentiate between one crop to the other using completely the SAR data. So this is one of the drawback here. So one drawback from one data product is an advantage in one data product, but one drawback in one data product is an advantage over the other. From here, this is the advantage to the another. So if we could integrate these together, we can effectively get a product where the drawbacks are overcome and we have a very good data sets to experiment upon. In the same way, we see the VV profiles also here. Here, one thing we can notice is uh, the the dip here. You see the red here. So in the month of November, the mulberry was totally pruned out and it was fallow, and again it started rising. So this dynamicities can also be observed, but interpreting SAR data is very crucial, very complex. Now the next case study I will be dealing with is with the Google Street View API. So as I mentioned, I went for the ground truth thrice. But what if the ground truth isn't possible at all? See, the area where you experiment should have the ground truth, because taking the ground dynamics into account only, we can have a proper understanding of what we are dealing with. If the ground truth isn't possible physically on the ground, but if we want to experiment it or if you want to validate anything, how the Google Street View images can be used for the ground truth is what I want to share with you. This I tried to experiment for some part of the Karnataka. This was the research done by the MIT people where they combined deep learning and street view imageries to map smallholder crop types. So you must be most familiar with these Google Street View images. If you take your Google Maps, if you click on a point, you get a 360-degree view of the image of that point. So with this, can we use this as a can we extract information out of this data, and can this information go to the ground truth? Yes, it is possible. So let us see how this can be done. So what happens is, first we have this road net. Let me explain how this Google Street View works. So Google Street View images are obtained where there is a jeep upon which a camera is mounted, and this jeep travels on the road network, on a major road network, and 360-degree images is obtained all over from for every point. The point distance is around 10 meters. So in 10 meters, you get an image of the 360-degree view. In the next 10 meters, you get the 360-degree view. So what this research they have done and they have implemented is, they have taken the road networks first, upon which they have extrapolated equidistant street points at an interval of 30 meters. And after that, they have taken the cropland and the tree cover mass, they have overlaid on it, and they have checked in which points there is crop land and tree cover. That points they have removed, because when there is tree cover, that would be blocking the view to the farmland, because along the side of the road, if there are tree covers, you can't effectively visualize what is on the farm. So that filtering is done, and we have the cleaned field points, and that points are actually on the ground. So now we have to pull the street view images for that point. So here you can use the Google Street View API. GSV stands for Google Street View API, and you can query the images from it. For every point, at that point, we have the Google Street View image where you can look on the either side of the road, where we can see the what crop is grown on the left and right of that direction. So we have Google Street View field images, upon which CNN model is trained using the iNaturalist data set, where This picture represents maize, this picture represents paddy, this picture represents banana or the mulberry or any other crop. That repository is from the iNaturalist. It is an open source repository. You can have a check with the iNaturalist. It has thousands of images from global scenario where different views of the crop land is. It's just like an image repository there. You can take the images from there that can be used as a training, and the Google Street View images can be supplied for querying, and you can obtain this. You can label each and every individual of the Google Street View images. So I will next in the next slide I will be showing how this is done actually. So after this, so we are converting the image to a point which is labeled. This point labeled goes into the model where a deep learning algorithm is run and a crop map is obtained. So this is what I was talking about. So if you see, this is the road and a car is upon a jeep, a camera is mounted, you get a 360-degree view of it. So at this point, you have the farmland images on the either side, left and right, with the lat long. It is geotag. For this image, if you run any ResNet or CNN algorithm with the training from the iNaturalist data set, you can obtain what is this, what field does this actually represent. Or in simple thing is, you can feed in this to the ChatGPT API, you can obtain the label for it. So this label goes into the crop type classifier model, and you obtain the crop map as the final outcome. You see the crop type classifier here, and it typically feels like a sugarcane. Yeah, you see the ground reference label is obtained as a sugarcane. So we have a point upon which we have captured an image. This image classification is run on this image first, which gives a label. This label is taken as an input, and a classification is run on the satellite imagery. So we are doing classification on both. One is on a camera image, and another is on a satellite image. So if we can't go to the field effectively, this type of ground truth can also be achieved, is what I want to focus here. So this is the iNaturalist repository which I was talking. It is an open source repository. So there is even noise, because when you give paddy or if you give maize, you might get result of images as such kinds also, where there might be a close-up view or a single crop. But the Google Street View images is typically on a large farms. So this is one of the drawbacks. So I want to show you the drawbacks also. I can't give a fancy scenario where everything can be done. So this is the challenge. So we have to work on how effectively we can overcome this challenge by having a collaboration with various researchers, where we develop such repositories where the farmlands or the crop images are labeled, so that can be used as a training, where we can develop one platform where we have a repo of all these uh, field images, where if we click paddy, we get thousands of images where the public can give an input to the images or download from it, where that can be given as a training. After they get an effective outcome, that can be transferred back to the online repositories. Like that, a common stack platform can be developed, is what I want to share with you. So after this, the third major thing I want to deal with is the crop yield forecasting. So using the machine learning algorithms like random forest support vector machines, you can analyze the remote sensing data to produce crop maps. And using the deep learning models of convolution neural networks and to process satellite imagery, we can do the crop health monitoring, the crop health analysis, a detailed crop health analysis that can be fed into the upon which the crop maps can be laid, and we can see how well the crop phenology or the crop health is monitoring, from the neural networks we can do the time series forecasting of it, and we can model the crop growth. So we have a crop map, we have the crop health, and we have the growth pattern. So if we integrate all this together and see what is the trend and how well, how good, how healthy the crop is progressing, we can effectively predict out the yield out. You see, This is the three layers I was mentioning to you. We have a crop layer, we have a crop map layer, crop health layer, and time series forecasting. So if we could combine all this together in a 3D CNN, 3D CNN is a spatio-temporal CNN, where 2D CNN uses only spatio-temporal, where in the first convolution the temporal is the time scale is dropped out, flattened. But in 3D CNN we have the pixel length, breadth, and even the time taken into account. So this spatio-temporal, where I'm stressing from the starting of the presentation, so this plays a very crucial role. And for you see, for every pixel you can obtain how much kg of crop is harvested. So yield production can be estimated out of it. So this is on a general scenario. So now let me go through the live project that I handled. So this was the STEC project, Yield Estimation Systems Through Technology, that was done at our center, Karnataka State Remote Sensing Application Center, where this was a part of the Pradhan Mantri Fasal Beam Yojan, where they wanted to develop technology intervened yield estimation systems where they can obtain the yield for that IU, the insurance units, which goes as an input to settle the farmer claims in the insurance. So what this model did was we took the model suggested was the semi-physical model. Semi-physical model eh, is a very simple model where the different scenarios like the parameters involved here is we take the insolation data, we take how well the photosynthesis is happening through the PAR data, photosynthetically absorbed radiation, FAPAR data, the fractional absorbed photosynthetically active radiation. It is simple. Let me put the sunlight is the source for all. So here this model is how effectively the sunlight falling on the crop is converted into yield is what we are monitoring. So the insolation data was taken as a as an external variable. The FAPAR data and the PAR data was taken, and the climate change or the trend which was happening or the stress which the plant was undergoing was through the temperature stress and water stress, which was accounted as a temperature scalar and water scalar. So we have the sunlight and the fractional absorbed photosynthetically active radiation. We have the water scalar, temperature scalar, which would collectively represent absorbed photosynthetically active radiation. So, given in a scenario where the crop is undergoing such an amount of stress in terms of water and temperature, with that amount of sunlight, what amount of biomass can it actually result into is what this model gives as an output. So, upon which the satellite derived crop map that was generated using the random forest was overlaid, from which we got the biomass. Whatever biomass we get is not the outcome. The biomass is just what the plant converts the carbon using the photosynthesis to carbohydrates in terms of biomass is what it grows. But yield is more specifically what we harvest. So the harvest index was obtained from the previous year. When this biomass was multiplied with the harvest index, we got the yield. So here, for developing the satellite-derived crop maps, the random forest algorithm, machine learning was employed. So this is one of the potential area. And now combining all these parameters on a single scale is a approach done here. But what if we could use some machine learning algorithms where with the historical data we can train the yield obtained and feed in this parameter so that we can develop a machine learning model where it can effectively predict out the yield is the food for thought in this presentation. So the final outcome here is the yield. So the yield was obtained on a pixel level. So after which we converted that the yield was obtained at an IU level. So every insurance unit had a yield. So I will show you the various products. So you see the PAR data set here. This was for the Raichur for the Kharif 2023. This is FAPAR. So PAR is what sunlight falls on the plant. but what sunlight falls on the plant won't be effectively utilized by the plant. So only a part of the sunlight is fraction absorbed photosynthetically active radiation is utilized. So this is FFR. After which we have the scenario of water scalar. As I was mentioning, what water is supplied, what stress the plant is undergoing, what are its demands, and how well it is responding to the water stress it is going on is represented in terms of water scalar. So this is represented using that LSWI converted to water scalar. And we have the temperature stress. This is the temperature scenario, the land surface temperature around. So integrating all this, we get the biomass. When we multiply the biomass with the harvest index, we get the yield. So you see for a Raichur district here, you get for every IU unit, you get a yield. The yield is ranging from 400 kgs per hectare to 8,400 kgs per hectare. So at an insurance level, getting this yield at an insurance level is very convincing because the normal yield estimation done through CC based might be biased in some situations, and some situations there might be interventions done. But using this satellite technology, the remote sensing and AI, we are unbiased in such a way that we don't know whose farm what is we are getting in a prior sense. At an outcome, we get the whole yield of the entire district. So we are not having any bias to any unit where we give out more or less. The whole thing is whatever the sunlight is falling on that part of the farm, that is effectively converted into the yield. So the technology-driven yield estimation system is an added advantage because there is less inclusion of human hands in between. So when there are human hands in between, there might be scenarios where the data might be hampered. So here, this is an effective technology, and we have seen a good results out of it. So this goes as an feed into the insurance claims, and a fair amount makes the farmer's life happy. The next and the important trending thing is the segment anything. I just want to show the one of the interactive GUI which is there with me now. So the segment anything. What is this segment anything? Oh, segment anything is a Python package for segmenting the geospatial data. So we had the SAM data which was used in the medical scenarios where medical images were monitoring. But geospatial people wanted to implement this using on a GIS scale. So they use this geospatial data. They use the SAM model on geospatial data and named it SAM Geo. So what does this do? So traditionally, as I was speaking with the crop classification or image segmentation has to be performed using a manual or semi-automatic process, which is time consuming and labor intensive. And it also requires huge amount of training data sets. But what does this SAM Geo do? SAM Geo, the SAM was developed by Meta AI, is a promptable segmentation where there is no need for you to give the additional training. It's just a GUI where you can feed in an image and tell it to segment. So let us see I will show you how this works. So let me present the entire screen. You see here, you see the image here, you see playground, playground buildings, road network, and other things. So you can see it is automatically segmenting. So what input does it takes? It takes the space, the shape of it, the pattern, the size. So all these the elements of image interpretation, it is taking inside it, and it is developing the segment model. You see how beautifully it is segmented. So what if we want to segment using an input prompt? You see, if this is a farm, and this is a water body, water indented farm. If you want to segment only this, you can give this as an input. You can pick points here. See, they are picking the points. And segment. See how beautifully it is segmented. So the traditional training, testing, everything is done in the background. This is the GUI where you can effectively harness what research or what innovation you want to do. Instead of concentrating more on developing a model, this is already a ready-made model where you can implement things. So what if you want to give a text prompt and say, okay, get me the buildings here or trees here. So let us see here. Yeah, let us see here. See, if you give trees as an input and if you give segment, see how beautifully it is segmenting only the trees out of it. Yeah. So this is the SAM Geo, which is very interesting and which is in the trend. So I just wanted to share this with you. Then, yeah. So what does now? Yeah. Now, what does this have a context in our application? We can do the field boundary mapping. We have vast amount of farmlands in a district. We want to see how the fields are demarcated instead of doing a field survey using the total station meter and meter pipes and all other extensive labor extensive instruments. We can do this field boundary mapping where you can fly a high resolution drone image over it. You can run a SAM model and you can get a field boundary mapping. Uh, and this is a huge repository in terms of mapping. The next one is the heat stress zone. Due to this climate scenario and the temperature anomalies in the globe, a part of the farmland, one farmer might be supplying uh, some part of the farmland might be undergoing water stress uh, due to the supply of water resource in a biased manner. So we can have this heat stress zone mapping. So using a thermal, if you have a thermal imagery upon which you take the SAM, or if you have if you do any NDVI profile, if you have any NDVI image upon which you do SAM, based on the texture and the pattern and the spectral signature involved inside it, the SAM model effectively cuts out the different types of zones. The next one is the irrigation zone identification. We can effectively differentiate which land is irrigated, which land is non-irrigated. The fourth one is automated crop segmentation. So whatever I told, the first three applications, the crop mapping, and leave the second, the first and the third application, the crop mapping and the ground routing, GSP based ground routing. If we could combine all these together, and if you want a generalized output, we can do this automated crop segmentation. You just give a spatio-temporal catalog image to the SAM algorithm. It effectively chips out different crop type images, segments. So finally, what is AI for smarter agriculture and water use? The integration of AI into smarter agriculture water use is not just a innovation, it is a necessity because taking the global context into consideration, we have to prioritize on the education and research funding in this domain so that we can ensure the geoscientists of tomorrow to be prepared to tackle the challenges of today. And what domains can we if we want to do research in the future? The three things what I feel from personally is the explainable AI, XAI, enhancing model interpretability, because whatever we have ANN, CNN, we know we give feed into the model does something, it spits out the output, but we don't know what actually internally it is happening, and explaining or readable of those scenarios are little different. So we can use, we have to see where we can experiment the use of XAI, explainable AI. The second one is the edge computing. So this reduces the latency of reducing the latency by deploying AI models on satellite on ground station instead of taking a huge image. For example, let me explain. If we want to do an analysis for a taluk in a district, say, we query an image which is of a size of 5 GB, and we subset it to a size of which costs of 40 MB. So you see the scale from which what was the requirement and what we downloaded. So if we could do the edge computing models where everything is done on a satellite and whatever you do, it's a quick delivery product. So you need not do all the processing here, where the all the processing are either done at this on the satellite or at the ground station, and you get an analysis ready product is the edge computing definition. The final thing is this is a crowdsourcing and citizen science. As I mentioned, if we could develop some repository where uh, we can have the whole images where we have labeled it to different crop types. Anyone can query and fetch the images from it, and they can run their model. After they run their model, and if they find any good results, they can upload those images back to their repository, and validation can be done. So this is just like an open source data repository where the research innovations is fastened because getting the data, doing the research, getting the data is itself a big research. So if we could develop in such a way where, especially speaking to the geospatial context, if we could do some things on that regard, then that is a very good trend in the upcoming area. The final thing is whatever we do should have a relation with the sustainable development goals. So space for SDGs is also I think we have to concentrate. And we know now the drone industry is booming to a very large extent, and even Modi announces AI agri drones for women self-help groups. So UAV based high resolution images is also a trending topic to be discovered. So finally, I will conclude by saying what is a tech pro? Tech pro, we have the technology here. We have various technologies, CNN, BITS, UAL, GAN, GNN, LSTM, UNET, MCD. And we have the problems. What are the problems? We have multi-source data. There is a multi-source. There is a need for multi-source data integration. There is a domain shift. There is complexity in the computation. There is cloud cover. There is imbalance in the data sets and bias in the AI model. So what we have to do is we have to blend this technology and the problem, and we have to be technically proficient. So what does this inspiration was drawn because if we have a problem and if we search for the technology, we might not be effectively choosing out a nice technology. Instead, if we have a technology scenario and if we could relate that to a problem and solve it, you can always do it. That's what Steve Jobs says. You can't connect the dots looking forward. You can only connect them looking backward. So you have to trust that the dots will somehow connect in the future. So let us have a collaboration with this trending technology so that the problems where we might encounter in the future might be solved. So yeah, thank you. And if you have any queries, you can reach out to me. You can ask me now also. And these are the references. I will share this with you. You can take a screenshot if required. Yeah. And I thank CMRIT for giving this wonderful opportunity to share my knowledge. Thank you, Sushma ma'am. And even I want to thank Dr. P.P. Nageswara sir for his guidance and encouragement.
Raghav,
Ah,
Raghav, one gentleman was
Yes, sir.
asking, what is
Uh,
NDVI? You can explain it.
okay, sir. Okay. NDVI, yeah, yes,
Ah,
Dr. Basuraj sir, yeah. NDVI is called
Someone has
normalized.
raised it.
Yeah.
Continue.
NDVI refers to the normalized difference vegetation index. What does this normalized difference vegetation index do? It takes we know that the satellite we know that the remote sensing does on a spectral band. So plants are more sensitive to red and NIR band. So if normalized difference vegetation index is a simple index where we have red and NIR band. It is the formula is NIR minus red divided by NIR minus red. So as the plant is more sensitive to wait, let me more than this, let me put this spectral curve and explain. Mm, yeah, I hope the screen is visible.
Yes.
Yeah. Ah, okay, you see here this is the spectral signature. Spectral signature refers to the how the different water, soil, or the green vegetation responses to the light which falls on it. So you see the reflectance in the band. This is the red band between point 0.5, red and RGB. So the plants are more sensitive to the red and NR band. So this acts as a proxy for vegetation. So normalized differential vegetation index is an index obtained from NR and red band. See, if you see here, we plants plants appears to be green because it reflects green is what we feel, but more than green it reflects NR, but that can't be seen because our eyes are only sensitive to the visible spectrum of the whole magnetic spectrum. So this is an NDVI is a special feature of plants where it stands out from the rest of the uh, other classes. Let me show. You see here, which are having high NDVI represent the plant or the green cover, which is having low represent the other classes. So this is just like a proxy to the whole. Yeah.
That's okay. That's
Uh,
fine. Fine.
Thank you, sir, for the wonderful presentation. I think you rightly said that integration of technology and the need, sorry, the need of water, agriculture, these are two things that has to be integrated so that we can sustain the resources for future generations. And using remote sensing and AI, I think your talk on your research work, I think it would have given leads to people who are working on what are the things that could be done. And I was actually interested about this water scale plots that you showed. Is that indicating how much water each crop absorbs, or is it how is it interpreted, sir?
Yes,
The
ma'am. How much, how much water the each crop absorbs, and what is its need, and what is observed is what is seen there. And
okay.
what are the shortcomings for it is it can also be felt. If it is on a range from 0 to 1, if it is 1, it is fully its tummy is full, it is fully contained. If
Oh,
it is
okay.
zero, if it is zero, it requires water to be fed in.
So that is done on a daily basis, sir, or how is that mapped for the?
Ma'am, it can be done on a daily basis, but taking the whole crop phenology to the account, we are doing for 8 days, 16 days, fortnight, or a month, 32 days like that.
Sir. So I think the use of water can be controlled based on the interpretation of the plots.
Yes, ma'am. Very true.
Okay. Thank you, sir. It was really insightful. I mean, I am not so much into satellite image processing, but the various options or various things that are possible with the current agriculture and water, they actually interest me a lot. I think it was very insightful. Thank you, sir.
Thank you, ma'am.
So, any participants, if you have any queries, you can please ask, sir. So I presume there are no queries. Yeah. Okay. Thank you so much, Raghavendra sir, for sparing time for the session and agreeing to handle one session in our FTP. And I would like to,
Thank you for the opportunity.
yeah, I would like to thank Nageshwar sir for yeah, giving your contact. It was a privilege to have your talk.
Thank you. Thank you.
Thank you, sir. I would request the participants to kindly turn on your camera so that we could take a quick session. Yes, yeah.
Okay.
Thank you, sir.
Okay.
Thank you very much. I request all of you to provide feedback. The feedback link will be posted in the chat window. Please provide feedback before you log off. And another yeah, information regarding the test and feedback. The test and feedback have to be done after the third session. That is before the valedictory function, not after the valedictory function. Test has been scheduled from 6:30 to 7:30 p.m. So you can finish the test and feedback and kindly join for the valedictory function. Yeah, the final feedback will be taken again from our session after the valedictory function. So I request you to please join the meeting after you have finished the test. Good afternoon, sir. I think our speaker for the next session is already there. Sir, shall we wait for a few minutes until the participants provide their feedback?